Alright guys, let's start with our next video for AP Environmental Science. We're going to do a quick review of some chemistry terms. Hopefully everything's familiar, and my recommendation would be that if we touch on something that you're not very familiar with, to look that stuff up, spend a little bit of time just refamiliarizing yourself with it, just to make sure that you know all the terminology that's going on. So real quick, matter, that's sort of where we always are going to start with chemistry. So matter has two things that matter, right? Okay, it has to take up space. Okay, sorry guys, you have to get used to my tablet writing. Okay, so it has to take up space. In other words, it has to have volume. Okay, and it has to have mass. Okay. So remember too that mass and weight are two different things. We kind of use them interchangeably a lot. Like we'll say weigh something on the balance when what we really mean is mass something on the balance most of the time. But remember, mass is, and this is where definitions start to get a little bit circular. Usually we define mass as the amount of matter in something. And so mass is essentially, we can think about it in our heads, it's how much something weighs. Now of course remember that changes depending on the gravitational pull, but as long as we're here on Earth, it's essentially a constant. And so for us, that's usually going to be in kilograms, okay, or grams, pretty often in chemistry class. So matter, anything that has mass and takes up space, okay. And so then some other terms that are going to come out of that. Atoms are our smallest building block of matter. Okay, doesn't mean that we can't break them down further. We all know that we can. That's what the Large Hadron Collider and all that good stuff is. We know that we can break those things down into protons, neutrons, electrons, all that stuff. But atoms are the basic building block because they're the smallest part of an element that maintains all the properties of that element. Okay, so what are elements? Well, essentially an element is a pure substance that can only, the atom is its smallest form and it can't be broken down any further without losing all of its chemical properties. Okay, so it's composed of a single type of atom and it can't be broken down any further. So, I mean, the easiest way is if it's on the periodic table, it's an element because it's the periodic table of elements. And by the way, if you're not already connected in some way to ptable.com, okay, make yourself a little link on your iPad. Hopefully you already did that at the beginning of the year. But that's going to be invaluable to you. That's like the best site out there for that stuff. Okay, so if we take like a step up from elements and atoms, we get to molecules and compounds. Molecules are the smallest component of compounds, okay? And compounds essentially are elements, two or more elements that are chemically bonded together. And actually, technically, it doesn't even have to be two or more elements. It has two or more atoms that are chemically bonded together, because you can have nitrogen molecules or oxygen molecules, and those are N2 and O2. All that stuff that hopefully you remember from your chemistry class lab. Okay, and then you've also got the atomic mass. Okay, now this is sometimes confused with the idea of mass number. Technically speaking, the atomic mass that's on the periodic table, not the mass number. Okay, the mass number is the number of protons plus neutrons. Okay, the number that's on the periodic table is an average. In other words, we've basically averaged out all of the different masses of that particular element. So how does that work? So for instance, carbon actually has three of what we call isotopes. Okay, now what is an isotope? An isotope is something that has the same element. Okay, it's the same element, so in other words, it has the same number of protons. Okay, all carbons have 6 protons, that's the atomic number. But it has different numbers of neutrons, and so therefore that gives it a different mass number. So in this case, this carbon has 6 neutrons, and this carbon has 8 neutrons. Okay, now why does the fact that we have different isotopes of atoms matter? Well, it really matters to us a lot. One of the most prevalent uses is because this is where we get the idea of radioactive decay. As you get more and more neutrons in the nucleus tends to get more unstable. And so to get rid of that instability, it wants to find some way to be able to kick parts of itself off so that it's not unstable anymore. So carbon-14 is a pretty good example of this. So that if you look over here in the second part of this, this is carbon-14, and it's a little unstable because it has a certain percentage more neutrons than it does protons, so it wants to be able to get rid of that. So essentially what happens is it emits a beta particle. That's what this is right here, okay? And when it emits that beta particle, then it's going to turn itself back into a nitrogen, a 14,7 nitrogen. That is a nice, happy, stable molecule or atom, and it's not going to decay any further under normal conditions. Okay, so having isotopes that have different amounts of neutrons tends to make atoms more unstable. That's why they're going to undergo radioactive decay. Now, a term that goes along with radioactive decay is that of half-life, and we hear this all the time. And it's a pretty simple term. Half-life just means that that's how long it takes for half of the original amount to decay. And so if we looked at this nice little graph here and we said, okay, so at the beginning here, let's say that I have 1,000 molecules of C14 or whatever, okay? Then after a half-life, when I get down here, I've only got 500 molecules left. And then if I went to another half-life, okay, on the graph here, then I've got 250, okay? And then I've got 125, and then I've got 62.5. Sorry, early in the morning. And so the time that it takes for that amount to decay, that's called the half-life. So like for C14, which is one that we're gonna see all the time. So for C14, the half-life is about 5,730 years, which sounds like it's a long time, but actually in the scale of half-lives isn't that terribly long. Something like there are lots of isotopes that have half-lives in the billions. So this actually makes it really useful for a couple of reasons for us in environmental sciences, because living organisms have a lot of carbon in them, and we can therefore calculate how old they are if we discover some samples by using how much C14 is left, because the rate of C14 is constant while things are living, and then when we know how much is left at the end, the percentage, then we can back calculate and figure out how old something originally was. So another really important thing about chemistry then is going to be about the bonding and the types of bonds that we're going to have. So real quick, just a real quick primer on this. Remember, covalent bonds are where you have energy or electron clouds that actually overlap. Okay, so you got two hydrogens here, and let's say that you've got an electron on each one. And so now, since their electron clouds are overlapping right here in the middle, okay, that's the bond. And so those two things bond together covalently because they're sharing electrons, and so we get a hydrogen-hydrogen bond. In the case of ionic bonds, so whereas covalent bonding involves the sharing of electrons, in ionic bonding we're actually going to have physical transfer of the electrons. So in sort of a classic case, if we just drew the Lewis dot structure for sodium and chlorine, okay, and remember Lewis dots are the valence electrons only, and that's what really matters in chemistry anyway, or those valence electrons that get transferred. What happens is this sodium is actually going to give up its electron to chlorine, okay? So now chlorine has 8, sodium has less than what it had. It originally had 1, and it's going to drop down to 8, but that's really beyond what we're worried about. But what really matters here in an ionic bond is since sodium lost a negative charge, it now gets a positive. Since chlorine gained a negative charge, it now becomes a negative, okay? And what do opposites do? Opposites attract. That becomes the ionic bond then for us, okay? And so the other type of bond that really matters to us are what we call hydrogen bonds. Hydrogen bonds aren't technically speaking an actual full bond, because usually when we say bonding in terms of chemistry, we mean atom to atom within a molecule. And hydrogen bonds are an example of an intermolecular force. It's different molecules that are holding on to each other. So like, for example, the most important example of this for us is water, because water is a polar compound. We'll talk about that in just a second. But what that means is that it's got a positive end and a negative end. And so the water molecules hold on to each other, not just the atom. And so what you're seeing here in the hydrogen bonding is that we see these we've got just a slight positive charge on one end, we've got slight positive charge on the end of the hydrogens, there's a slight negative charge here on the end of the oxygens, and so between molecules we get this hydrogen bond here, and it's kind of hard to see the way that these are drawn here, but basically if you've got an H2O molecule here, and another H2O molecule down here, okay, then the way that we usually denote that is we draw, instead of full bond lines, we just draw some dashed lines in between, and that's going to show that those things are holding together a little bit. Now, that's going to have a lot of effect on some of the properties of water that we're going to talk about. So what does that come down to? Polar and nonpolar, hopefully these terms are relatively familiar to you, but basically it just means that polar, when we talk about polar, it doesn't mean cold. Polar means that we have charges on different ends of the molecule. And so this is obviously a water molecule here. And so what that means is that on this end, on the oxygen end, we've got a negative charge, and then on the two hydrogen ends, we have positive charges. That's because of electronegativity differences between them. Okay, oxygen's very electronegative, hydrogen's not very, and so the electron cloud gets pulled mostly to the oxygen side. And again, that's a chemistry thing that doesn't matter as much to us, but what matters is that we know that it's polar. Something's nonpolar, meaning that it doesn't have any charge if it's essentially symmetrical, like this is. This is a methane molecule, CH4, and so it's very symmetrical in 3 dimensions. And so there's no real way for any one end to have a charge because it's all the same atom on the end. It's a carbon in the middle and 4 hydrogens on the outside. And so therefore there's no polarity, there's no charge. Now that has some pretty big implications because what that means is that water molecules are going to exhibit hydrogen bonding. They're going to want to stick together. Methane molecules, they don't really have much attraction for each other, very minimal van der Waals forces. And so they're not going to want to hold together nearly as much as water. And that plays into a lot of the very special properties of water that we'll get into a little bit in our next